This. No, I do not. Just for one thing. One thing I'm ever gonna need. Yeah, I do.
Question about the point. Sure. When I the system with more material and stresses, which I expect.
Okay.
That should be versions, that's for each one.
You only need to do one, that's fine.
Okay.
So
One for the gel.
exactly, yeah, one for given material, given boundary conditions, and what is in the same.
Yeah, I thought that would be Jesus.
Technically, I mean, you made a good observation, you should do multiple,
Okay.
but you know, first if we're.
Or if you want, I could just hold on to
Just count
it.
practice. Just one, for one.
I'll return them all. Oh, just to get all of it? Yeah. I'm gonna return them all this Friday. Oh. Okay. Alright, well. It's so simple. So just kind of that. Thank you so much.
This is
But I look at the strap. Yeah.
I
think that's way better than mine, though.
Yeah.
Were you able to get the last one? The solid element? I explained that I had to take away the extra part. I explained that I even have to. Like. Or not. Crumble. Yeah, so I was like, no. Have something grow.
Well, they said I wanted that. No, yeah. I mean,
Oh, yeah. I haven't been. I have to put the things on the other side. And then you like anything. For this movie?
Just so you guys.
Hello. Yeah, like.
This is what we're coming to now, we saw him again, like, when you're.
Yeah.
That one, the fun area.
Oh, yeah, that's what.
Okay, that green area in the middle,
And he's like, so there.
kind of, there's that.
That's the alpha squirrel.
That one and. It's exciting.
The guy that's sitting there.
That's squirrel. owns it. That's squirrel owns the quad. He just letting you know. Oh, yeah.
No, I feel like it's just, you know, like windows and stuff. Yeah. I just wanna know this.
I mean,
That's my prototype that I'm taking on Saturday. Yeah, I chose to. Yeah, but it's solid, easy. Gotta be fast. And then does that, right? Hopefully, I just want to present and get this shit over with, like, hopefully fast, because I was studying. I don't want to be. Why am I seeing easy? No. Yeah, don't, yeah, because I'm staying here. Yeah. Show and I'm. All right, confirm. Maybe we, oh. Now.
Okay, it's 5:30. Let's get started. All right, good evening, everyone. How's everyone doing today? Good. Finally getting some good weather. I think things are gonna heat up, I think, from here, so we see more sunlight from the YouTube. Okay, so we're taking a little bit of a detour this week. I know last week I said that we're gonna start to prep for activity 5. But because the midterm project, you know, I feels like it's kind of getting in full swing. I've been getting a lot more questions on that. I wanted to give you guys kind of this week to kind of work on it. We'll do activity 5 next week. Just because, you know, the week after next week is spring break, and so, we'll do activity 5 right before the spring break. The activity, the intro project we do during spring break, and then activity 5 we do the week after we come back from spring break, so, you know, not everything is just kind of staggered at once, so. I think my fear is that if we did activity 5 this week, I think I probably still wouldn't have it due till after the midterm project anyway. So I didn't want you guys to kind of work on activity 5, like, all right, that was like 3 weeks ago. So I'm gonna push activity 5 until next week, so just kind of flip things around, and so this week's just gonna be a lecture week. And then, you know, we'll kind of pick things up with the activities next week before we leave for spring break. Okay. Okay, so the topic for this week is we're gonna start to talk about non-linearity finite element analysis. So we're gonna talk about what that means and kind of how that changes things, because everything that we've done up to this point, we've basically assumed linear behavior. So we'll talk about kind of what things can introduce non-linearities, how that can affect your results, and how to actually deal with them. And this will become really, it's a lecture week, so it's, you know, you're just going to hear me talk for an hour and a half on Tuesday and Thursday, but I think this week is actually particularly really interesting because we're finally done talking about meshing. So no more meshing after last week. Okay, any questions I can answer before we get started for today? Any questions with the midterm project activities? Okay, all right, so let's go ahead and get started. Okay, so the topic for this week is non-linearities and finite element analysis. Okay. So non-linearity is probably a term that's mentioned in passing in a lot of your previous classes, particularly in your graduate courses. And kind of the way to sum up what a non-linearity means, non-linearity makes things very difficult to solve, kind of put it very simply. Whether you have nonlinear terms in math, nonlinear terms in your governing equations, in your engineering courses, you know, non-linearities in FEA, non-linearities make things very difficult to solve, and FEA is kind of no exception to this. So up to this point in the class, you know, everything that we've done so far has assumed linear behavior. And linear is kind of how the human mind kind of behaves naturally. So, you know, with linear behavior, we kind of assume that everything that has kind of a cause and effect relationship, that kind of still follows the same trend when you modify the inputs. Okay. Let me give you an example. Something that, you know, we've seen in this class, right? And so if you have a cantilever beam, so let's say that we apply a load of 1,000 kilonewtons on this beam, right at the very end. I know I use the cantilever beam a lot. It's just the easy example to think of when you're thinking of structural. Okay, so after you apply that 1,000 kilonewton load, if the deformation or if the deflection of the beam is 3 centimeters, in a purely linear setting, if we were to have the amount of load, so if our load was reduced to only 500 kilonewton, you know, instinctually in our mind we say, okay, our load was cut in half. That means our deformation should be cut in half as well. Use our load to half of what it was, so 500 kilonewton. our deflection is gonna also be reduced to 1.5 centimeters, centimeters here, okay? So this is what it means to be purely linear. So everything kind of exists on this linear line where, if you have the input, then your output is also gonna be have, same if you double it, same if you increase by 50% or you reduce it by 20%, things like this, okay? So this is kind of what our mind typically expects when we think of kind of linear behavior. And you'll be surprised at, how many, this is kind of the default way of thinking kind of about many things, right? So for instance, let's say you're watching, the Lakers or something and they're up by 20 at halftime, right? Your mind would expect, okay, the Lakers win by 20. That means by the end of the game, they should win by 40, right? Because that's kind of a linear extrapolation. But, if you watch the Lakers for any given time, that that usually doesn't happen. So they sometimes they end up winning, but maybe they only win by 2, and it's kind of, you kind of move some hairs off your head. Or if you're cooking something, so let's say that you have your stove onto medium, right? And then you turn the stove on to high, you're like, okay, my food should cook twice as fast now because I'm applying twice as much heat. But that of course doesn't work out that too, right? So thinking linearly, that's kind of how we naturally kind of think of things, but reality is often kind of different than what we expect. And structures in FEA is kind of the same thing as well. So in reality, pretty much all deformation that is experienced out in the world is nonlinear deformation. There's nonlinear responses. Okay? So that means there's not a linear relationship in terms of how much load that you apply and how much stress that results or how much deformation that results, right? So there's going to be a nonlinear relationship. So all stress strain deformation relations are like this, okay? So that linear elasticity relationship that we talked kind of a lot about at the beginning of the semester, right? That's not exactly true for most materials, okay? Now that is true. It is generally true for kind of a regime of kind of what we call small deformations. So if your deformation is relatively small compared to the overall dimensions of your part, of your geometry, then it's pretty safe to assume linear behavior. It's still an approximation, but it's a very reasonable, very accurate approximation because if you actually went out and measured it, you're probably going to get more or less kind of the same thing. But if in truth, if you really wanted to model it correctly, you need to incorporate this nonlinear behavior. And as your deformation gets larger and larger, you need to kind of incorporate this more and So large deformations is probably going to be the most common case that you're going to run into, kind of in your everyday life as a finite element engineer, introducing non-linearities. But there are other possible sources of non-linearities as well, and so that's what we're going to talk about today. So today, we're going to talk about, what are the sources of these non-linearities, both from large deformations to the geometry, to the boundary conditions, to the constraints, to the materials, right? So we'll talk about all of those. We're going to talk about kind of the best ways to handle it. Now we're going to be talking about ANSYS specifically, just because every software kind of has its own unique tools in order to deal with the non-linearities, because it's usually not a default setting. And so we're going to focus our discussion on ANSYS, but just know that most other software have a way to do this. And we'll kind of see kind of what the differences in the results would look like in those cases. Okay. Okay, so everything we're going to talk about this week, these are things that you can also include in your project. It's not a necessity, and so we're kind of going over this lecture a little bit late in the process because I know a lot of you have kind of already made a lot of progress on your projects. But if this is something that you want to incorporate in your project, definitely feel free to do so. And I think it'll be interesting to kind of see what the differences in the results are. Okay. Any questions on any of this so far? Okay. All right. So let's talk about some of the sources of nonlinear behavior in FEA simulations. Okay, so we're going to talk about kind of three major sources, three of the most common ones, but just know that there's other possible sources as well. The first one we've kind of already talked about, and probably you were aware of this even before this lecture, which is large deformations. Okay. So with large deformations, this is going to cause the structure to actually distort significantly. And that's kind of why we kind of have to incorporate that within our FEA. Which, duh, it's like one of those, statements where it's like, yeah, large deformations is going to cause large distortions. But, this actually has quite a few different results or kind of effects on our simulation. So one is the mesh, right? So on the one hand, when you have significant distortions of your geometry, that's also going to cause your elements to also distort. So traditionally, when you do structural FEA or just any structural analysis in general, it takes what's called kind of a Lagrangian approach, which means that your structure is going to deform in real time, and that's going to affect kind of how things are actually applied in general. Right? So it's not kind of a virtual deformation that the structure is actually deforming within the computer itself. Okay. And so for FEA, that means that if you're going to make your mesh based on your original geometry, if you have significant distortions, that's going to make your mesh kind of distort as well. And that may cause some problems where, on the one hand, you may have some elements that start to really kind of get really poor quality. Or in the worst case, you may get elements that actually start to kind of clip into each other or kind of overlap each other, which is obviously very bad. So that's kind of one thing. The other thing is that, when you start to get kind of large deformations, your material behavior often starts to change as well. So you have to start to account for things like plastic deformation. Right, so we've kind of talked about in this class that once you start to get past that linear region, your stress strain relationship starts to change as you get into that plastic region. So this is probably going to be the number one source of nonlinear behavior, especially when you start to get to kind of the extreme loading conditions. Okay. And certain applications, or this is kind of a daily reality for them. They have to kind of. Okay. Number two. So the number two source of nonlinear behavior in FEA is what I call topology nonlinear. Okay, so topology nonlinearity, this is what happens when you have a change in connectivity of your mesh as your simulation goes on. This most often occurs when you have an assembly of different parts, okay? So if you recall, from our last couple of activities, and some of you have already experienced this in the project as well, right? When you have an assembly of different parts, you have to define within ANSYS how those parts are connected, right? So most commonly, we've used a bonded support or a bonded connection between parts, so that the parts are exactly bonded together. But there were other options there too. And and back then when we first introduced this, I promised you that we would talk about these different options. Well, this is the time. And so maybe not today, but probably on Thursday, we're going to talk about kind of what those different options mean and how they can introduce nonlinearities in our system. Number three, we're not going to get into too much because this number three kind of, honestly, it kind of deserves its own lecture series on its own. Probably, 2 to 3 weeks of this is material nonlinear. Now, this goes beyond kind of what I mentioned in point one here. So in bullet point one, we said that when you have large deformations, oftentimes that's going to result in changes in your stress strain relationship. But that's still within kind of the realm of what I call kind of a traditional linear elastic material, right? If you remember when we talked about material properties, I think maybe it was like week 3 of the semester, right? We said that, we kind of talked about there were lots of other interesting material models like hyperelastic material models that have an inherent nonlinear relationship between stress and strain. So again, we're not going to dive too much into this. We may kind of just mention a few of the common options that are available. But just know that, there's a lot of really interesting work that. And kind of the cutting edge technology nowadays in terms of manufacturing and of parts is to do things like composite materials or, additive manufacturing type materials. And so, of course, all of that stuff has to be translated into the finite element domain as well, okay? So there's kind of a lot of really recent interest in doing this, both from a manufacturing and a modeling perspective as well. So, yeah, a lot of great stuff there. If we have time at the end of class, at the end of the semester, I think it's a very relevant kind of current topic that's being discussed in the community. Okay, but for now, we're going to focus mostly on point 1 and point 2 of this section. Okay, and kind of the main thing that you'll see, throughout this section on Thursday is that whenever you introduce non-linearities or when you want to account for them in your simulation, it's going to drive the cost of your simulation up. So that's kind of something to be aware. It's very easy and very easy for me to say here that all of these non-linearities are important. You should always account for them in order to make your simulations accurate. But a lot of times you don't have that kind of practical budget. When you're doing these kinds of simulations. So each of these non-linearities, whether you account for them or not, is a choice, right? And it's a choice of whether you want more accuracy or more cost. So it's not always clear, which is going to be correct. So it's kind of your job as kind of the engineer to really decide from a case by case basis whether non-linear is important for this situation. Okay. Any questions on this so far? Okay. All right. So let's go point by point here, and let's dive deeper into each of these. So let's talk about large deformations first. Okay, so let's talk about large deformations first. And so, we kind of touched on it just a bit earlier, but when you have large deformations, it causes your geometry to distort, sometimes significantly. We call this kind of geometric. Another way to kind of call these is geometric nonlinearity. So a lot of the computations that finite elements is going to do, really strongly depends on the orientation and the geometry of each of the individual elements, right? And so if they start to get really distorted, then that's going to affect the quality of your simulation as well. Okay, so, for relatively small deformations, we typically don't worry about this because, with a small amount of deformation, your mesh elements are not really going to distort all that much. And so, it's not really a concern, when you have small elements, your element is going to be roughly the same quality, roughly the same skewness, both before and after you apply the deformation. Okay. So just to give you an example, let's say that we start with a relatively, well-formed element. Right, so an element like this, I would say, is generally very good quality because it's, roughly, the sides are parallel, it's a good shape, it's good volume, right? But as you apply a load, so let's say we're applying a shearing load onto this element here, okay? And then eventually, as we ramp up this node more and more, this element is going to start to distort. Right, so you might go from something like the first location there to the second example to the third example, right? And in the worst case, let's say you keep ramping up this load, you end up with an element, that may look like this, which, as you can imagine, is very, very skewed, right? So you have some nodes that are very, very close to each other in this element, and some nodes that are very, very far. So this element here, I would start to get concerned, about the quality of the solution that it is. Okay, so how do we deal with geometric nonlinearities, or how do we make sure that this doesn't hurt our simulations? Well, it turns out, this type of linearity is actually the easiest to deal with. And really, you only have to just kind of toggle the setting, and what that setting does is it actually does something very, very simple, but also very clever at the same time. So to kind of help ease this kind of transition and to make sure that the elements don't distort more than it needs to, the way to deal with this is actually to apply your loads in small increments, or to kind of slowly, incrementally increase the load, and then have that result in your margin. So basically, the idea with this approach is that, instead of kind of having all this very large deformation that happens at once, and to kind of risk, these elements become distorted in one particular area, by doing it slowly, you kind of, only just do a very small amount of deformation relative to the previous one. So each step, you know, you can kind of almost consider each step to be kind of only a step, small deformations. And so you kind of preserve that kind of linear behavior kind of step by step. You just do this in enough consecutive steps so that you estimate these large deformations a bit more. Okay, so this is kind of the main way that we'll approach this, and that's kind of what we'll spend the most time on. Okay, but before we talk about that, I do want to say that in certain extreme cases, so let's say that your deformation is so extreme that there's just no way for the mesh to kind of handle this without, you know, completely folding it over itself. So for extreme cases, there is an option to do what's called remeshing, you know, as your simulation progresses. And so if you have a situation where the deformation is so extreme that there's just no way, then you can only okay. So this is very common for situations where you have a very kind of flexible solid. So let's say you have rubber or something like that that can kind of go through kind of extreme deformations. Or in other common cases that you have kind of any kind of fluid structure interaction. So you have kind of a flag that's kind of flapping in the wind. Right, and so in those cases, it's pretty much a necessity for you to have to remesh in order to get a good quality solution. Okay, so that sounds very clever, but you know, remeshing is also extremely expensive. It's probably one of the most expensive things that you can do in the middle of a simulation. Because if you can imagine, you know, if you're doing this a lot, right? Think about how long it takes for you to produce your mesh, you know, for just one simulation that you're doing now. And so think of trying to do that 1,000 times throughout the course of the simulation, and suddenly the cost kind of, you know, balloons up like crazy. So this is an extreme case. I actually had one student in the past kind of work on the project remeshing, but we had to kind of change our approach completely just because it was such a nightmare to kind of do this. It is possible to remesh, but you know it's usually kind of a last ditch resort, not something you want to do right. Well, let's talk about that first option first. So let's talk more about, you know, what happens when we kind of apply our loads incrementally, or increase them in magnitude incrementally. Okay. So when you apply the loads incrementally, you know, you kind of never do a situation where you go from rest to large deformation all at once. Okay. Let's look at a graph here. So the simplest way to kind of increase your load incrementally is to do so in kind of a linear ramp. Okay, so let's say that the ending goal is to apply a load of 1,000 kilonewton. So in this situation, we kind of apply this load all at once, and so there's kind of just one, there's kind of two data points here. So there's one data point at the origin, and then one data point at the very end. So we just kind of ramp up immediately. Okay. But if we add a lot of intermediate data points here, so let's say that we add points just like this. Now, in between each step, we don't increase the load by any more than, let's say, 1,000 kilonewtons. So individually, within each step, we effectively have kind of a small deformation linear deformation solution. So in this case, you don't actually have to make any specific changes to your material model, to your governing equations. In this case, we're still using the exact same linear elasticity equations that we were using before. It's just that we're applying it in kind of a clever way to account for these non-linear, make sure that they're not too extreme from step to step. And that's very appealing because, if traditionally, if you did want to use, if you did have very large deformations, you would often have to change your material model to kind of accommodate. But if you just did just pure linear elasticity, it's not going to compute well. So with this kind of incremental approach, you can actually do that. And the reason this works, and the reason it's kind of so clever, is that when you have nonlinear behavior, it actually depends. Your nonlinear behavior actually depends on the time series or the time history of how your loads are applied. And so by kind of applying these loads in kind of several substeps, you can kind of account for these nonlinearities much more easily. So within each step, you don't have an extreme amount of deformation relative to the previous, right? So the way this kind of works is that when you have these kind of incremental approach, right? You start by applying a small portion of the load, so let's say 10%. And so you apply that load, you observe the deformations, you save that as the geometry. That's going to be now the starting geometry for the next step. And so the next step, you're going to increase the load by, let's say another 10%. And so you're going to increase the load, you're going to observe the deformations, save that as the starting point for the next step, right? And you keep continuing this until you reach the full amount of load. And then by the end, you're going to have a very large amount of deformation. And it's going to be computed much more accurately than it. Okay. Any questions on this so far? Okay. All right, so if you had a pure linear simulation, so actually, all I would say all the simulations that we've done so far in this class have kind of been in that ballpark of small deformations. If you did this for a pure linear simulation, it doesn't really matter if you did this in 10 substeps or 1, you're going to get the same result. Okay. And in fact, I think a few of you actually tried that. So there's a setting within ANSYS itself called large deformations. And so when you turn that on, it basically switches the solution mode to something like this, right? And I think what a lot of you saw was that, for the bike crank or for the signpost, right? It didn't really make a difference whether you had large deformations turned on. You have 1 increment, you could have 10 increments, you could have 100 increments. If your simulation was going to be linear anyway, then you're always going to end up with the same result. Okay. But if you have a situation where you are going to have large deformation non-linearities, it does matter how many increments that you have. And in fact, that's something that you actually have control over. You can actually change within ANSYS itself. Because again, in each, the more increments that you have, each increment is kind of approaching more and more kind of linear cave. Okay. So the more increments that you have, the more accurate simulation. But of course, you can imagine each increment that you add is basically increasing the amount of simulations that you have to do, right? So even just the basic setting. So I think the basic setting within ANSYS just does 10 increments, right? That actually increases your computational cost by 10. Because you're doing 10 sub simulations instead of just the 1. Question is. You could, yeah. So that's something you can do as well. So you can actually check and see, You can basically do a conversion test in terms of how many increments you get with the converged solution. And eventually you're going to reach a point where if you add more increments, it's not going to improve your solution anymore. Yeah, good one. All right, so how you actually apply this in Anthos is that there is a setting within the analysis settings. There's a parameter in the analysis settings, which is called large deformations. Okay. So we haven't really done too much with that tab in our Anthos activities so far. A few of you have asked questions about it, and we kind of talked about it. But if you look under your solution, kind of in the subtree on the side, there's one tab called analysis settings. So in there, there's kind of a lot of for this class is mostly kind of miscellaneous settings that you can set to kind of modify the simulation. But one of the most key settings that you can do there is you can turn on large deflections. Which is kind of a very vague kind of a setting, if I'm going to be honest. But what it does is that it turns on this kind of gradual incremental load increasing. And so it's going to take all of your loads and then it's going to increase them sequentially or incrementally, from 0 up until its maximum, and it's going to do so in a set amount of steps. Okay. We're going to do kind of exactly kind of what we did here. And you do have control over this. And so in case you wanted to kind of modify or adjust how many steps or how many increments that you're going to take in this kind of non-linear kind of approach, the setting for that is called, let's see. So I think by default it's called auto time stepping. So with that setting, Anthos is going to decide how many increments or how many kind of sub intervals that is going to be used to increase your load by. But you can change this, and so instead you can change this to defined by. And so by doing so, then it's going to give you the option to change something called what's called a subset or substep. And under that setting, you'll be able to change how many iterations or how many subintervals you want to have it as you ramp up the loop. So that gives you a little bit more control over kind of how many subintervals that you want. If you wanted to, you could do a convergence test here. Okay, so how is this going to affect your results? So if you kind of do this correctly, so if you kind of you kind of set your subintervals and you set them to a sufficient number so that the nonlinear is captured well, then what you should see is that your deformations that you get are going to be larger in magnitude for the same boundary conditions compared to if you left all these settings off. So, for this graph here, we're explicitly comparing, we're keeping our loading the same, right? So we're not changing the loading between these two cases. But the only difference between these two is that on the one hand, I've turned on this incremental loading as well as the large deflections. The other one I have not. Okay. So you should get something that looks like this. And so if you did not turn on any of these settings, so you left it just purely linear, right? And so you're just going to do all this deformation just in one step, right? You're going to get a simulation that probably looks something like this. 2 data points, you start from rest and you end up with just a result like here. But if you were to turn on this kind of load incrementing as well as the large deflection, it's going to change. It's going to change the behavior of it. So initially, right? Initially, you're going to have kind of this linear behavior because this is kind of the regime of kind of small deformations, and so the overall deformations on the beginning part of that curve are going to be smaller, right? But eventually, there's going to be kind of a point where this kind of departs. And so on that red curve there, that's kind of the deformation that you should expect with all these settings turned on. So incremental load adjustment as well as the large deflections. And so you can see at the end there, once we've kind of fully applied the load, we have a larger amount of deformations than if we just did everything. Okay. Any questions on this so far? Yeah.
When you select automatic time setting, does this show how many intervals there is?
It does, yeah. So when you look at the results with the automatic time stepping, it should actually be available right now too. So there's kind of a graph at the bottom. You may have to enable it. I can kind of show you next time. It'll show you kind of how many data points there are in the steps that there are. So I think by default, it chooses about 10. That's the default, but it may change it based on the case. But yeah, you can observe it in sometimes there's a table that shows you that. Okay, let's talk about probably we'll talk about the topology stuff. Well, we'll see. Let's talk about the residual, because I think that's an important concept as well. I don't normally talk about this with my undergrads, but I think it's important to talk about with. Okay. So when you have nonlinearities in your simulation, usually that means that your equations are going to be nonlinear as well. Okay, so like we talked about kind of at the beginning of class today, the equations that we're solving for structural mechanics, they already have some nonlinearities in them. So that's kind of always been true. But when you have kind of a relatively small deformation case, these nonlinear terms or this nonlinear behavior in the equation is usually kind of very negligible. Okay. But by doing things like increasing the amount of deformations, you have large deformations, you start to have topology nonlinearities, you have a nonlinear material model, these nonlinearities in the equation kind of become more pronounced. Okay. And so I think probably the better way that I would kind of say that, when I say that we're introducing nonlinearities, that means, we have things like large deformations, we have, topology nonlinearities, things like that. So as these factors become more and more important in simulation, then those nonlinear terms become more and more pronounced. In other words, we have to account for them more and more accurately. But we can't actually solve the differential equation with these nonlinear terms. Even mathematically, it's impossible. And so to actually solve these equations, we rely on a trick called linearization, which basically means that we take each of the nonlinear terms and we approximate them with a linear version of those terms. If you've taken 438 or 538, you probably kind of know what I'm talking about, what this actually means. But it's an approximation. And a lot of times, when you have small deformations in your finite elements, usually this is not that big a deal. Usually this is. But as you get, more and more nonlinearities, this becomes more and more of an issue. Right, but this is a necessary step because otherwise, without linearizing, we can't actually solve the equation at all. So there's lots of different ways to linearize an equation. So in fact, math theory is kind of filled with these. You can go on and on about the different methods, but the method that's used within ANSYS itself, and this is kind of a popular method for FEA in general, is a method called the Newton-Raphson method. But Newton-Raphson might be a familiar name to some of you. With the use of optimization within last semester, it should hopefully be familiar. So you might be thinking, how do we use the Newton-Raphson in this scenario? Because it would seem to apply. Well, the details of that I think are kind of I'll save that, or I'll say that's covered in 538. I think that's probably more. But kind of the upshot of that, or kind of the result of that that's relevant for us, is that this results in a solution, right? So this allows us to get a solution to our nonlinear equation, but it may not be exact. And so in other words, by applying this Newton-Raphson method, we're going to incur some errors. These errors are kind of unavoidable. You kind of have to do this, right? Because those errors are needed to actually solve the equation itself, okay? But then how can we check to see, whether these errors are relevant or not? Because there's a difference between having really big errors and there's a difference between having, very negligible errors. Well, the good thing is that, we actually have our equation, right? We know what our starting equation was, and so we can take this solution and then plug it back into our original equation. So actually, it kind of follows this kind of flow chart. I think it's a little bit easier to explain. Okay, so the start for this is you have a nonlinear partial differential equation. Right, you have a nonlinear partial differential equation on an arbitrary geometry that we cannot solve. Right? So, the way that we solve this is first we apply finite elements, right? We take our geometry. And we mesh it into simpler shapes. And so that's going to get us kind of a mesh, okay? Right? But that's not all we need. And so even on those elements that we have there, we don't have everything we need to solve the equation. Because remember, our equation is still nonlinear, right? So we've kind of taken care of the differential equation part. We've turned that into algebra, but we have a nonlinear algebraic equation. So in order to solve this, we have to linearize the equation. So we apply Newton-Raphson. So what we get from this is a linear algebraic equation that we can solve for the solution. Keyword here is linear. And so at this point, we have linear algebraic equations, so we can solve it. So let's we can just use math and solve. We get the solution to our linear system, which is good because we have a solution, but we don't know how good it is. So, what we can do is we can take this solution and actually plug it back in to our original nonlinear partial differential equation and see how good the match is. And so we plug it back in. If we're very lucky, then we're actually going to get an exact solution here. And so there's going to be 0 errors, right? We plug this back into the original equation. We get left side of the equation equal to the right side. We're all happy. We can go home, drink beer or something, have fun, right? Most of the time, that's not going to be the case. So most of the time when you plug back in, right, there's going to be some discrepancies in the equation. The left side of the equation is not going to quite equal the right side, right? And that's normal. That happens all the time. That's a consequence of not only applying the FEA, but also applying the linearization or the Newton-Raphson. So these discrepancies or these differences in the solution that results from applying our numerical techniques, this is what's often called the residual of our solution. So the residual, kind of the formal definition of the residual is the difference between the approximated solution, or I should say, kind of the errors that result from plugging in the approximate solution back into the original governing. You do any kind of computational science, finite elements, finite volumes, CFD, computational heat transfer, the residual is a very important point. And oftentimes, when you use a commercial software, the software will tell you what the residual is. Okay. ANSYS is no different. So ANSYS does tell you the residual. It's just kind of hidden from most users just for kind of a better user experience, but otherwise. And this residual is actually often used a lot because if the residual is too high, what you can actually do is you can actually iterate on this again. So you can re-linearize around your new solution and then run through this situation again, and that's going to end up with the reduced precision. Okay, I'm kind of oversimplifying the process a bit because this process is all about the theory of what's called linear solvers. And so if you ever get a chance, kind of another topic that I would want to get into more probably semester, but how you actually solve a large system of linear equations after linearizing, there's a lot of theory beyond this as well. So actually kind of the real flow chart kind of goes something like this. After you plug it back in, what you do is you re-linearize. And so you re-linearize around a new data point, and then you solve your equations again, and then that's going to end up with a more accurate solution than before. So oftentimes you're going to do this several different times, and all of this, by the way, is happening within one sub-increment. And so this is kind of the iteration within the iteration itself, okay? So this kind of ends up with kind of a large, large amount of simulations and large amount of calculations that have to be done. Okay, and so the last thing I'll go over today is, how do you actually read this residual information and how do you know when it's good, okay? Now, this terminology is a little bit confusing because we've already talked about convergence in another context. But convergence, a lot of numerical techniques is all about convergence to some degree. Convergence of your mesh, convergence of your linearity solver, all that stuff. So this setting here is called convergence. Okay. So this information is accessed within ANSYS itself. It's just, again, kind of hidden just because it's not the most pleasant at if you're a casual user of ANSYS. Okay. So the way to check this is to go under. So after you run a simulation, there is a tab there called solution information. And you can check, there's a few different convergences that you can check. And so you can check, the one I often check is called the displacement convergence, which basically tells you how well your displacement is being computed relative to the original equation. And so, looking at this graph is a little bit confusing because it looks very similar and kind of the terminology is very similar to our mesh convergence tests, right? But it's important to note that when you're looking at these graphs here, this is not, the mesh isn't changing. This is all taking place within the same simulation. This is just how well, your linearization, how well your non-linearities are captured in your solution, or not. So the graph may look something like this. So on the vertical axis here, let's say we have called the displacement residual. So the displacement residual is kind of a measure of the error in your displacement solution, as you iterate more and more. And what you should see is that there's going to be some dotted line. So that dotted line there is going to indicate convergence of your solution. So we want the residual to kind of go below this line. So that tells us our errors are going to be low. And ideally, you should have a graph. It may fluctuate a little bit, so it may kind of fluctuate up here a bit, but eventually, it should kind of die below that line. Okay. And so if you have a graph if you have a convergence graph like this for the residual, that means your simulation is well converged and you're able to capture all of the non-linearities in the solution. So you should go back and check some of your simulations, and for your project, this is something that you can check as well, just to make sure that you are kind of capturing all these things, and residual. All right, any questions on this before we wrap it up for today? Okay, all right, so that's all we got time for today, and so when we come back on Thursday, we'll start talking about topology, non-linearity, so all the different types of contacts that you can have in your simulation, okay? And how that introduces non-linearities, and then we'll finish up these measurements. And so thank you guys for coming today. I hope you guys have a good rest of your evening, and I will see you guys on Thursday.